Welcome back. I believe my spouse would say happy garbage day. Because it was delayed, you see, the holiday pushed it a day back. So she didn't get to say that yesterday? Yeah. Did she tell you that? It wasn't garbage? Okay, so you get to hear it. What a great way to start class with garbage. Anyone ask you how this class is? Garbage. That's a good word for it. How's it going? I was describing with another one of my colleagues, week 3 of the semester is usually the part where stuff just gets really unhappy. Why? It's like week 1, hey, we're back. There's sort of excitement, sort of getting used to things. Week 2 is sort of, how am I going to get enough sleep? And week 3 is, I really dislike a lot of this stuff. So I get it. If you're in that dislike phase of the semester, I still like you. I'll try to make the impact on your lives as minimized as possible, but still try to teach you what you're trying to learn. Okay? Okay. A couple announcements. I like to start with those. I always make lists of things because I'm very scatterbrained. Number 1, I am having office hours today after class. So please, if you're wanting to talk, please come see me. Next Wednesday will not have office hours. So I've moved them to Monday from 12 to 2. I will be on, I also have a link, a Zoom link for it, which I'll circulate via class announcement on Icon. So, you don't have to be in present if you want to talk in office hours, just first come, first serve. I'll have the Zoom window open, but I'll be physically present in my office in room 210B in the Casma suite. Okay? Great. Class Friday ends at 1:20, so we have a shortened class on Friday because of administrative stuff. I'll just use the word stuff. What was the word I started off with? Garbage? Stuff. I'll call it stuff. I put up a formative assessment number 2. 2 questions about lecture last week. Try them. Do you see it? Can you access it? Okay, you've seen it. Remember, if you make an honest attempt, you get full credit. Honest attempt meaning something. Even I don't know is an honest attempt, I guess. So I don't want to penalize you for not knowing. But you get full credit. Tomorrow's homework 1's deadline, 2 screenshots, that's it. Right? In terms of planning, I know we talked about this. I didn't have homeworks listed as when to go. I'm planning a homework that will come out next Tuesday and be due 2 weeks later on that Tuesday. So that's just planning. But that's nothing too bad, nothing too serious. But it will be actually using the result of homework 1, which was so successfully installing Stan, hopefully, in a Bayesian analysis. Okay? So if I'm going to sketch out a few more plans today, we're going to keep going on the lecture that I started last time about the ideas of psychometric models. And the following lecture for this will be an introduction to Markov chain Monte Carlo methods. So that's where we really start doing some Bayesian. But it will feel like a step back because it'll be using linear models, linear regression to do so. But today's lecture is going to talk about how psychometric models are really just linear models themselves. So I'm trying to link all that together. Do you have any questions for me before we begin? No? Anybody there online? Okay. Oh, geez, that was loud. Man. All right, let's begin. I want to move forward to where we left off, or at least where we started class last time. And so last time we started talking about sort of latent trait theory, and one of the guiding principles I like to talk about is the idea that a lot of psychometric models are just regular types of analyses, linear models or generalized linear models. Just some of the variables haven't been observed. And so if you think of it that way, if you think, what would this analysis look like if I had observed everything, particularly the latent trait? That is a good guiding principle for how to conduct what we do. But also, if you think really hard about that, if I'm talking about what we're going to see today, the psychometric models are linear models. Where else did you learn linear models in your training? You learned some in
intermediate stats.
What's that?
Intermediate stats.
Intermediate. And you covered regression, covered analysis of variance. Then some of you may have taken design of experiments. Well, it turns out whenever you're collecting data, design is also important. And the same thing works with psychometric models, right? If you believe me that my premise that psychometric models are essentially linear models, multivariate linear models, and you had to worry about design for the other analysis you do, it reminds you that you should also worry about design for psychometric models as well too. So just to tack that on. So we talked about measurement, formally designed, why are we measuring things, how do we do it? We assigned numeric values to some type of observable thing. I talked about measurement of mass or length the last time, because we want to move a table and see if it fits somewhere, right? Or fits through the door to get it out of the building, or something along those lines. The same thing with psychological constructs. However, because we can't measure them directly, we have to actually define a set of things they're related to. And you're going to see that's why I keep talking about linear models. The latent trait is related to the things that you're making people do on an assessment, on a survey, a questionnaire, and so forth. And I think I left off by saying, we have to remember, though, there's sort of a few other parts of it. We have to somehow quantify the observable behavior. So if someone selects strongly agrees, sometimes we give that a 5 or arbitrarily. Or we just call that as the unique category. We also need to then aggregate all of those behaviors into some estimate of the quantity we're seeking to measure, the latent variable itself. And then we have to figure out whether or not what we just did really reflects what we intended to do, validation. We don't think about validating length as a physical measure, but it kind of works the same, right? The size of this table, if my tape measure worked the right way, on either of those, it should fit through the door if it's smaller than, right? It's kind of the same premise, we just don't think about it for physical measurement. And finally, the last thing I left you with was, if you were to do secondary analyses with these latent variables, you have to remember that unlike some physical measurements that we make, like length, the latent variables are measured with error. We quantify that in different ways. In item response theory, you may have heard of something called the conditional standard error of measurement, where each latent trait has its own standard error. You may also have heard about that in versions of classical test theory or test theory as well, 4-parameter beta, something like that, defining the standard error. We often then try to flip that amount of error into some type of index, sometimes called reliability. This program is unique in that many of my colleagues here, if not most of my colleagues here, look at reliability very critically. If you read empirical articles about reliability, you'll say, reliability is Cronbach's alpha. And here we're all like, we study it. I'm like, yeah, alpha doesn't work very well. I knew that before, but then the different modes of reliability or breaking down error in different ways, like generalizability theory would be. So there are different ways of talking about it, but we have to remember there's error in each of these measurements. And error doesn't work well with linear models, right? Error can cause lots of problems in linear models. I wouldn't say lots, but some. How are we doing? Is this a good summary of where we left off? Okay. Remember, this is like philosophical stuff. I'm getting to equations. Once I get my equations, I feel really good. But philosophical stuff like this, I feel very out of my element. Even though we're all training to have degrees in philosophy, right? Something like that. Okay, so let's talk about measurement models. The last slide talked about the process of measuring something from a latent variable point of view. A measurement model is the glue that takes the observations, the data, and ties it to the thing that you're trying to measure, the construct or latent variable. They are a distinguishing feature of psychometric models. They are models. They are theoretical projections, if you will, of reality. Right? So just like any other model that you'll see in a quantitative field, that means good things and bad things. Right? What other aspects of life are you used to seeing models in? And then not, outside of psychometrics and latent variables, or anything in statistics. Let's just say life.
Sleepiness.
There's a model for sleepiness?
Probably.
Oh, see, I want to see.
Oh, like something specific?
Yes.
Architecture?
Architecture, very good. A model of a building, a structure. I was going to say, I'm looking at my watch here, and it tells me the temperature, which is the current measurement, but then it tells me what it's going to be. It's going to be, 75 degrees Fahrenheit at 8 o'clock tonight. That comes from somewhere. A model, right? Weather model. Weather models can do some things well. Weather models can also not do some things well, right? The forecast of the heat dome over California right now, very, very accurate. The forecast track of Hurricane K, which is off the coast of Southern or Baja California, accurate for a couple hours, but then what happens after 3 or 4 days, right? So what I'm trying to make a point of is that models in some ways are nice because they help you verify reality. You can check them, you can see which ones work better, but models also leave a lot to be desired because they are just that, they are models, right? So now that I've convinced you of that, why are we doing this class, right? They're all models. Anyway. So the psychometric models we use are often called measurement models. I like that term measurement models because it's the idea that it's where the latent variable, the construct that is not observable, meets the things that are observable, the things that measure it, the items, the responses, the behaviors, and so forth. So they are measurement models are the mathematical specification that provides the link between the latent variables and the observed data. It literally is that. If you look at the equation for each of these, on the left-hand side of the equation, where we usually put the outcome, is the data. On the right-hand side of the equation is the latent variable, somewhere. What we're going to come to find out is that equation is one part of the deal, but in the Bayesian context, it's not the full thing. We need to know the distribution for the data, and then we need to understand its distribution function. What part of that function is where the latent variable starts to impact the data themselves. But measurement model does all that. Now, you may hear a bigger context of this. There's measurement models, and then there's another part of a model that sort of, depending on which part of psychometrics we talk about a lot or don't talk about it at all, and that's something called the structural model. How many of you have heard of structural models before? Right? The structural model describes how the latent variables, either the distribution of the latent variables or some other types of regressions on that distribution. So for instance, you've heard of structural equation modeling, right? Structural equation modeling typically has components of which that are measurement models, right, where we define latent variables, and then components of which where those latent variables predict other things or are predicted by other things simultaneously. So let me ask you an odd question. Those of you who understand structural equation models understand measurement models to some point. Would IRT fit under that framework? What's the structural model in an IRT sense?
The responses?
No, the responses are data. So anything with data, for the most part, is a measurement model, not entirely. So let's talk about this way. Structural model, in just a plain measurement model type of standpoint, describes the distribution of the latent variable. So in IRT, if you're taught IRT from a operational testing perspective, what do you do? What is the distribution of theta in IRT often?
Normal.
Normal. What's its mean?
0.
Standardized. Mean 0, standard deviation 1. that takes the place of the structural model, and it's almost so uniformly used that you don't even think about it. However, that's a choice, and that's a model, it's a structural model. And so,
Structural model is the distribution of theta.
yes,
Oh,
a model for the distribution of theta.
oh yeah.
In our case, a mean of 0, standard deviation of 1. It actually is, IRT and CFA in this case is a really unique part of this, because in Bayesian language, we would actually say that distribution of theta is a prior distribution, and the hyperparameters of those we fix to certain values. Right? But these are all synonyms. So I'm using this to sort of talk about it. I'm trying to expand your horizons about what you may know. That doesn't mean what you learned about IRT is incorrect. It's not, most likely. What it is that when you look at IRT as a measurement model in the context of all the latent variables, IRT, the word we use for it, prescribes a very specific type of data and a very specific type of trait. But at some point, the labels start to break down. As we saw with the example when I had binary items, continuous items, and whatever. What do we call that? I have no idea, right? So at some point, it becomes models and assumptions and so forth. All right, we okay? By the way, what I'm going to teach you, I hope challenges you to think differently. But if you think I'm saying something wrong, challenge me back. I would love to show what I'm thinking and try to explain better or convince you that what I'm saying is correct. And here we go.
Well, no, it's not. So the prior for distribution for IRT is the normal distribution, but is there like theory or something that supports that ability is normally distributed?
I think the theory is lazy.
Okay.
No, I shouldn't say that. It turns out the normal distribution is a super convenient distribution to use to build things. And there's a number of reasons why that's the case. We're going to see that normal distribution models can lead to quickly building really complex models in Bayes' sense that have conjugate priors, which makes sampling a lot easier. That doesn't have to be that way, but it does. But I think that's part of it, right? From the beginning, we need to make a decision about that. It needed to be pinned down. So we said that. Now, if you think about the estimation of the latent trait theta, you don't actually have to make the assumption that it's normal, right? You do have to assume some type of scale, a mean of 0, standard deviation of 1, but you don't have to assume normality. And that is a key difference between what we would do in Bayesian, where we would have to, and what you might do in non-Bayesian settings, like maximum likelihood or otherwise. But yes, hope that helps a little bit.
Has anyone started with like a non-informative prior and then when, to see if it turned out to be normal after a while, or?
Yeah, I mean, yes. So there's this other feature at work. The debate about priors generally, although not always, is a debate about sample size or information in your data, I should say, right? The more sample size tends to mean more information. Oh, and what sample is in this case is different. The sample size for theta is actually the number of items a person's taken. So if you give somebody 300 items, you'll start to reach something called asymptotic convergence. That likelihood that we would use in ML is the same likelihood that is the basis of our posterior distribution, right? The likelihood, model data likelihood times the prior. And so the model data likelihood will overwhelm the prior at some point. The question is at what point when? And so when you argue about the type of prior, what you're really arguing about is that point at which infinity happens. Or maybe not infinity, but the convergence starts to take place, where the likelihood on one side overwhelms the prior in another in a product sense. All right. Any other questions? Is this entertaining? No. Lisa was telling me everybody was tired yesterday. I'm sort of getting that vibe today. Do we need explosions? Comedy? I'm not the one for comedy.
Musical numbers.
I'm not the one for If you wanna like see competitive coding, I'd at least have a fighting chance for that. But nobody's like esport. What's your esport? Coding. Yeah, not gonna work. All right. Trying. Okay, so it turns out the form of these measurement models look very different. And I remember this, like when I was in my first semester in grad school, and they started putting model equations down for IRT versus CFA, they look completely different, don't they? Right? There's no way that you'd say IRT is this and CFA is that. But that's only because the model equations are, remember, one part of it. The model equation is actually, if you think of those of you who've had generalized linear models, it's the mapping of the continuous part to the range of the distribution, right? So in IRT, because we have binary data, we have to map onto the mean of that distribution is a probability. We have to map onto that. And that's why you get that crazy looking either logit or inverse logistic function to make it work, right? In CFA, we don't have to map because the outcome's continuous and the right-hand side and the left-hand side are continuous. There's no real function there at all. And so you start to put those together and you're like, ugh. But once you start to think about it in terms of distributions, right, you need a mapping onto the mean, sometimes the variance of the distribution, but you have a distribution function. Each of these variables has a distribution function that gives us a likelihood, and that's the key. That goes into the model likelihood. So even though they look very different, that's only because of the mapping, the range of the data. They still have likelihood functions, they still have values that go into them. So what do measurement models need? They need a distributional assumption about the variables at play. Right? So each measurement model, typically the names of which are sort of given to the same types of distributions that show up with the variables that you're trying to model themselves. We'll see that, but let me just give you, we'll see it more specifically in a few slides. Let me just tell you. In factor analysis, the distributional assumption is that the outcomes, the data that you collected, are normally distributed. In IRT, for binary items, the distributional assumption is that those are Bernoulli. Right? For non-binary, for discrete polytomous items, we might call them, we might say that's either a categorical distribution, or sometimes called a multinomial distribution. But each of those are types of distributions. Right? So remember, you don't often think about that when you're in the class itself, because the class is all, or the family of model is all making the same assumption about variables. But remember, that's a choice you get to make. That's your data. Then there's that linear or nonlinear form that predicts the data from the traits. Technically, that's predicting features of the data. The generalized linear model, that link function, is applied to often the mean of that distribution, right? So we know a Bernoulli, the mean of a Bernoulli variable is a probability. We take that probability divided by 1 minus the probability, it turns into a logit, and we predict the logit, right? That's usually what happens. But the key in all of this is that the observed data is being predicted by the latent variables. And that's where I'm telling you to remember what these would be like if the latent variables were observed. Latent variables predict observed variables in our measurement model. How's that sound? Questions? Boring. Yeah, yes.
Yeah. So in this case, first of all, we assume that we have a latent trait, and there are some indicators that can measure this latent trait in this population or sample. But at the same time, we're assuming that this observed data, the response values, will be predicted by the latent trait.
That's right.
So it's like a loop.
It's crazy. We have to define the latent trait by the set of variables and then pretend that that latent trait is predicting the response to those variables. Yes. What do we do? How do we do that, right? Is what you're saying?
Uh-huh.
Yeah. That is exactly the problem. How do we do that? It seems like a loop. The variables define the trait, but the trait predicts the variables. Turns out, in a broader sense, this is where it fits nicely into Bayesian. Because what we can end up using is sort of the idea of the conditional distribution. When we write out the measurement model, we're saying this is the distribution of the data conditional on the trait. What we're after in terms of measurement is actually the distribution of the trait conditional on the data. That's a posterior distribution. And that measurement model is, we can use Bayes' theorem effectively to build it. Right? The measurement model is now the model data likelihood. If we add in the prior distribution of the trait itself, now we have a method by which we can sort of assume a shape of a posterior for the thing that we didn't observe, even though we have it there. Now the loop part, yes, that is a problem, because how do we know that we did it well or correctly? And that's where the next step of validation, or the very first step of validation occurs, which is what we call model fit. We have to check that the model fits the data. I like to lump that into a validity argument, but does that help?
Yeah.
Yes.
Yeah, so I thought about this yesterday in Lisa's class as well. I remember that regression requires the predictors have no measurement error.
Mm-hmm.
But in this case, our predictors are latent variables.
Oh yeah.
And aren't they supposed to be that easy?
Yeah. Yeah, the prediction, I like to say we have to pretend it's as if we have observed the latent variable. That'll give us the form of the model. But, and this is the key, it's not exactly a linear model because of that. And so what we really need to do in this methods that we build to try to estimate, particularly the model parameters, right? We're talking about when we form that regression, there's parameters that link the latent variable to the outcome. We have to use care. We have to do certain things in certain ways to ensure that we are allowing that unreliability, if you want to call it that error in the trait, to not be forgotten. Hope that helps.
So it's not exactly regression going from the latent to the...
It is actually regression. It's just regression when the thing is not constant. Sort of a measurement error regression approach. It's especially that in a Bayes context, because every step, let's think of a Markov chain. Remember, Bayes doesn't always Markov chain, but for most of this class we're going to use Markov chains, MCMC. At every step of the algorithm, we have a guess as the latent variable. But if we build the algorithm correctly, then that latent variable will move. So every step is a little bit different. So it's like doing a bunch of regressions with different values.
Can you explain this measurement error thing when we get to the equations?
Hopefully.
Oh.
I'll probably be able to explain it better once we actually get to the MCMC. So maybe a few weeks from now.
Also, I have no idea what MCMC is other than, it's like a numerical method for estimating.
Yeah, we call it
Is
magic.
that right?
Magic. There's two M's in there. It's something magic.
Okay.
Maybe you can help me make something. No, MCMC is a brute force method for determining the shape of the posterior distribution. And by that, what we're basically saying is if I told you right now, I want to see what a normal distribution looks like. We've all studied the normal distribution. We could draw it, whatever. But let's imagine I didn't have those tools. I only knew that I could somehow randomly generate data. What I would do is generate hundreds of thousands of pieces of data and make a smooth histogram, a density plot of it. MCMC is the generation of the pieces of data in that case. We're going to create a very smooth histogram of the posterior distribution to get a shape for it. Hope that helps answer that a little bit. It's
kind of like the Bayesian version of estimation.
It is an estimation method that absolutely relies on Bayes because Bayes' theorem makes it work. So MCMC is a Bayesian method, but not all Bayesian estimation is MCMC. That helps a little bit. All right, how are we doing? Lots of terms. That dictionary, I need to go to the dictionary and update it on the icon site, so we start adding these, right? Okay, so let's talk about measurement models versus other measurement techniques. If you are like me when you went to grad school, I didn't know about measurement models. I'd heard of exploratory, what was called factor analysis, but turned out it was exploratory factor analysis, mainly principal components analysis as an undergrad. And I thought that was advanced at the time, back in the 90s. However, what I thought of about measurement was basically, okay, I give out a survey, usually a Likert scale, because I'm in psychology, I wasn't looking at education. And I want to score, so I add the scores up. Right? That's very different from saying, I need a model to provide the score itself. Right? So a lot of the world will do what I just talked about. They'll enumerate the item response score, right? So, you've got your 5-option Likert type data. Each option gets an integer. There's your enumeration of each item. Or in a cognitive test, students either answer an item correctly, answer incorrectly. Correct answers get a 1, incorrect gets a 0. There's your enumeration, right? There it is. It's like I made these slides. So the latent trait score then is formed most often by adding the responses together. We add them all up. Turns out, I'm going to call this the add stuff up model, and I put a little asterisk there because please see Lisa Hoffman for a more explicit definition of stuff. She uses a 4-letter word there. I don't. Right? I mean, you're used to this. You give a survey, you got to do something with the data, so you add up the scores. When you're done adding them up, what do? You do something with them. You put them in a regression, you put them somewhere else, right? Is there a model involved in that? Not explicitly. You didn't go and take the process that we're talking about by defining the distribution of a variable and then make the prediction function and so forth. But it turns out, as it turns out, I even said those slides. I'm telling you, it's like an iterator reliability with me and my slides. Those of you who took me last fall when I was giving this with Lisa's slides, it wasn't as high. But these are my slides. So the naive, I call it naive adding together of items, actually implies a measurement model. Right? You didn't know that you were doing that, but you are. And I can show you, if you want me to take the time, that this is called a parallel items model, right? Where that has very, very strict assumptions that are actually testable in a measurement model framework. More on that in just a moment. But very rarely met by real data. Parallel items assumes that each item has the same variance, and each pair of items has the same covariance. Okay. Anybody ever seen the parallel items covariance matrix in the real world? Ever seen ever done that? And let's just think. That means if you want to, I rarely work with covariance. I usually work with correlation, and you can always turn a covariance matrix into a correlation matrix. So how many of you have ever seen a correlation matrix of, let's say, 20 variables where the correlation was identical for all pairs? It's pretty naive, right? That is parallel items. And when you add items together and provide a score from it, that score is based on that assumption. Yes?
Is that what rash modeling is based on?
Close.
Okay.
Close. More on that
Okay.
a little bit later. Rash model actually, it is a parallel items model. However, the way the score happens there has a nonlinear function to provide it. So it's mapping, well, we'll get to that. Let's get to, ask that question in the IRT section of the course. Okay? But yeah, if I told you, hey everybody, I got this survey, and not only but I'm gonna go add it up when I'm done, because I can guarantee you the correlations are all the same. Would you laugh at me? Yeah, right? This parallel items, if you think about it, expressing it in a model terms, it's very convenient to do in a CFA framework, something with a normal distribution, because you can work out very quickly what the expected covariance between items should be and what the expected variance of an item should be. And if you do that with a parallel items model, you can show that the trait score you get from CFA has a correlation of 1 with the sum score. Just turns out you have to make every item parameter identical across all the items. Yeah, like that's going to happen, right?
Like the difficulty, discrimination, all of them.
All of them.
Oh, wow.
Yeah. In CFA, it's actually the two that matter are the factor loading and the unique variance. So adding things up is really common. In certain parts of social science, you'll even see people who have what they will call structural equation models, or chunks of that structural equation model are the sum of items. And that sum of items ends up being a parallel items model. They call it parceling sometimes. Have you heard of item parceling? Not a great idea. So what could go wrong in that case?
What if an item is bad?
Right, all items are treated the same. How would you know it's bad? Exactly.
Everyone got it wrong, but
Well, that's one way. Look at the mean of the item. So it turns out, this is one of the reasons why we like models. Is because, first of all, even when we're not using them, we're actually using them just under really strict assumptions. And the second is that a model can help us understand the impact of each item in a way that will work. Now, let's imagine we have the Likert data and we fit a CFA. It's approximately true that if the model fits the data, the scores will be very heavily correlated in one versus the other, like 0.95. But that doesn't mean, there are a couple things wrong with that. How we quantify the error in the score is definitely off. Right? So our reliability estimate is definitely off. But beyond that, if our scores are important to give to people, like we're making decisions about them based on what we're doing with the scores, we're ordering people from high to low, people are reversing order if we don't get the assumptions right. That's bad, particularly if those people need to use that score to go to grad school or have a career, start their professions. So what I'm trying to argue for with this is it turns out, even when you don't think you're using a measurement model, you actually are using a measurement model. So it's good to dive headlong into it because you can tell when things start to go awry with the model itself. How's that sound? I'm trying to persuade you about models. Okay, any questions? How's the pace of this? Okay, I never know if I'm going too fast or too slow or boring you. If I'm boring you, I'm sorry. It's just not exciting. When I was younger, I was like, no, I'm exciting. And now I'm old, I'm like, no, I'm just old. Just boring and old, all right? But hopefully informative. My trait is that you'll take boring and informative rather than exciting and informative. No, never mind. Anyway. Let's talk about these latent variables a little bit, right? Because they don't exist. So, do you ever, when you were learning intro statistics, we often talked about variables and their levels of measurement. Right? It's a very old concept. There's this field of mathematical psychology, mathematics, psychology, even in education somewhat, called axiomatic measurement. I don't know if you've ever heard it before. It's sort of the logic that is implied by the measurement that we're doing with variables. And the labels that you hear applied to this is very old. I don't know that people in that very small field would think of these the same. But I'm going to use them because they're very uniform in how we teach this. We talked about interval level variables before. Remember those? Interval level variables are thought to be continuous. Right? There's a numeric score to it. There's not a fixed zero, right? And the term interval is used because the units of quantity are the same across the scale itself, right? So what do I mean by that? If you compare a score of a 2 with a score of a 0, those scores are 2 units apart, right? Those same 2 units apart would be the same distance between a score of 0 and a score of -2. Right? So we're saying the distance is the same in terms of units across the scale. Cool with that? Most of our models are trying to estimate interval level latent variables. That's a choice, though. Not always do we use it. We could have ordinal level variables. For ordinal, like a rank, like first place, second place, third place. We know first had either more of or less of something than second, but we don't know how much more. right? Second had more than third. We don't know how much more, so we can't say the distance between first and second is the distance between second and third. But we can order them, ordinal. Sure enough, the field that I'm most known for, the research I've done, diagnostic classification models, the latent variables are actually ordinal. We often define a latent trait as having two categories. And in an education sense, and I think it's a misnomer, something we shouldn't do, we say one category, we give students a cognitive test, like a math test. Students are going to be either masters of the material or non-masters of the material, which is not a good label, like from a scientific point of view. I think that requires extra validation. But that's effectively what happens. Masters have more ability than non-masters. However, we don't know how much more. And even moreover, all of the masters, we can't distinguish between them. They're all homogeneous. All the non-masters are homogeneous. So an ordinal level latent trait is possible. Now, why would we use such a thing? Because interval sounds so good. Well, sometimes we just want to know a person's relative standing. Or, in the diagnostic model sense, it turns out these ordinal level variable models are actually what we call classification models. They use a classification methodology. And it turns out it takes far less psychometric information, in our case, far fewer items usually, to consistently put people in the same group. So we might say, I want to give my students some feedback, but I don't have time to give them 40 items to put them on a continuum. I'm going to give them 10 items and roughly order them into two groups. And on the basis of that, I'm going to instruct certain groups with certain things. So that's a decision that you make. Because remember, psychometric models are all about time. We use psychometrics in a lot of different places. So that's one way of thinking of it. Any questions on that?
Don't you lose a lot of information if you rank people? Because like you said, like you don't know the difference between the ranks, so you're kind of losing that ability. Then also, like, philosophically, that just feels weird that you're...
Well, let me go a step further. Here's what's happening in a lot of the latent variable models. I'm going to get my pen out here. Okay? So we have a continuum. Let's call it theta. Okay? All right, and here's 0, here's 1, here's 2. All right? So Nathan, I give you an assessment, and I can tell you're an excellent student. So you're going to be at the high end of this assessment, right? This is a cognitive test, right? So here's Nathan right here. All right? And it turns out when I was a student, I took that assessment, and here I was, like right here. That's Jay. All right? So you're like, oh, Nathan, you are like 1.5 units higher than me. But we forgot an important feature of this. That is, this assessment, that latent variable, it's only our best guess as to where you are. There's error involved with it, right? And if it's like, if we used IRT with it, that error usually has a function that's kind of gets more and more error as you get closer to the tail of the test. So if we were to put a confidence interval around your score, it might look something like this. Right here. So your score is actually somewhere between 1 and 3. Now let's imagine we put a confidence interval on my score. Right here. This is my interval right there. So now, are we ordered? Most likely yes, but not necessarily. In fact, there's an overlap in our intervals. And that overlap actually makes this order what we would call mathematically a weak ordering. Meaning we can't actually order between you and I, even though the best guess of the data looks like we could. Now, if we gave an infinite set of items to you and an infinite set of items to me, that interval would get smaller and smaller and smaller and smaller. But who has the time to do that? So we are assuming an interval level, but in reality, we're not getting it. Right? I have an odd question for you. Does anybody know it's sort of related to this. I promise there's a point. What's the minimum GRE score you have to apply for grad school here? Does anybody remember?
300.
I'm sorry?
300.
300. Okay. So let's imagine you take the sum of verbal and math, right?
Yeah.
So let's imagine you take the GRE and you get 300. What's the probability you're at or above that cut?
The probability what?
The probability that you are at or above that cut if your score is right at the cut.
Yes, it depends on the confidence interval.
Let's assume the GRE has a long enough assessment so we can make assumptions about the score itself. Let me ask this question. Those of you who are going to be practicing psychometricians really need to know this question right here. If your score is right at the cut, what's the probability you're at or above it based on your error?
Is it 50-50?
50-50. If you assume a long enough assessment, so you get this asymptotic convergence of the likelihood for theta, it becomes normal or symmetric. And you're at the mean. So how about that? Have you ever thought about cuts that way? Think about that, right? If you have a student at the cut, that means they only have a 50% chance they're at or above it. How does that make you feel? Doesn't make you feel good, does it, right? Did anyone tell you about that, about the test? Yeah.
I mean, maybe not in the GRE example, because I think probably individual departments setting those cuts are a little arbitrary, but like, let's say in the case of the state assessment, something where we have cuts for proficiency and advanced.
Yeah.
Isn't that taken into account when they set those cuts?
Oh, have you ever been part of the process where they set the cuts?
No, I only do after.
I have. I've run a couple standard settings.
Okay.
And it's eye-opening, right? So what they end up doing is trying to understand through several different methods where a cut should be. Some of the names of those are Angoff, reverse Angoff, modified Angoff, bookmark, I think they might use here. But the process of cutting it is a policy decision that's actually debated depending on, I mean, standard settings work in different ways. One I was involved with had educators, I was in Kansas at the time, educators from the state across all levels of school, teachers through administrators. They sat around a table and they looked at all the data of where the cut should be based on these methods. And then eventually they made a cut. That cut was made on a Friday afternoon because everybody needed to get out of town and get home. Okay? And it was, I've heard it said that in standard setting, those cuts are arbitrary but not capricious, right? So they're trying to make it with the best of intentions. But there's nothing about the data that suggests a cut at all. And it is the case that if you have a student whose score is right at the cut, it's a 50-50 shot as to where they're at. And on the flip of that, I've also served as a peer reviewer at the US Department of Ed, evaluating state assessment programs. There are a couple states I evaluated where, for several grades, they made cuts such that if a person was in the middle of the middle cut, that was like a 3-category cut for one of the, actually 4. Anyway, they were in the middle cut, the average standard error, the reported conditional standard error at that point would extend beyond either side of the cut behind it. Meaning that it was effectively a person who was right in the middle of like the middle category had about only a 30% chance of being in that category, or 33%. It was almost like seeing it in different ways. So the whole process of cutting and standard setting is an add-on that has very little mathematical support for what we do. But I hope that answers your question. So yeah, anyway, think of it that way. When somebody's at the score, like when you're looking at, if you're ever in my shoes and you're evaluating students to come in, or people based on scores, where you set your minimum threshold, if someone's at that, you only have 50% chance of getting higher. But anyway, error is a big deal. That's why we end up having different psychometric models. You want to go with one more add-on to this? I know we've had this conversation. Let's imagine this right here is where I needed to get into grad school, right? So we could pretend my little hypothetical distribution of my ability looks like that, right? On average, I'm below that. But if I have the money to pay the GRE, how much does the GRE cost these days? Too much. So every time I take that assessment, you could pretend that I'm bouncing around my interval, right? So I take the assessment, and I get my first score, and it's right here. But let's say I have unlimited resources when it comes to money, and I take the assessment again, because I really want to get into this grad school. And I get a score that's right here. So close. I take the assessment a third time, spending more money. I'm right here. And finally, I take the assessment the last time, right there. I made the minimum threshold. What's the institution do? Is that fair? Is that accurate? If I'm the institution, if I'm a psychometrician at the institution, I want to average those scores. Because that average will give me a better estimate of my ability.
The institution will take your highest score because it's going to impact the rankings.
And so now, let's talk bias and fairness. Because we can have an unbiased assessment that implicitly biases towards those who have the means to take it multiple times. And that's not an assessment problem. That's an institutional problem, a policy problem. So anyway, things to think about when it comes to error. This is what gets us going. What you're going to see, the beautiful thing about Bayes in this class is when we estimate these latent traits, you're going to visualize the error in the distribution. You will see it. You will plot it. You can take two students and compare them. And when you do that, you're like, wait a minute here. Right? So occasionally we'll have people who work for the GRE or with the GRE, on the GRE even, and ETS wants to know, hey, how do we make our product better? Two things I say. One thing, first of all, give me a standard error with every score. They don't.
And they make less money that way.
They would, because can you imagine selling your product that says, you're going to take the GRE, you're going to take the GRE, you're both going to say the same amount, you both may get the same score, but one of you is more accurate than the other. That's what will happen. These will be different forms, even though we try to make them roughly equal when it comes to that. When it was much worse when it was the straight computer adaptive test. But anyway, that's what I want to say. So I'm on a riff on this, but the reason I'm on a riff on this, where did it go? Here it is because there are rationales for trying to use different types of latent variables in measurement models. And so the argument against the interval level is that people misuse the data because they're not given enough information about error itself. I think that's part of it. Ordinal is one of those things. There, I just said that. There's also another level, nominal. Do you have different types of students? Okay. Do people use different strategies when applying to items? Do people have specific deficiencies when it comes to cognitive tests or different patterns of responses when it comes to other assessments? This is a categorical variable. Have you ever heard of these before? How about a measurement model within it? Probably haven't heard of that before. What if I said latent class analysis? Or finite mixture models? Factor mixture models, mixture-Roche models. These are the types of things that go there. Mixture-Roche model actually combines continuous and categorical. But it's the same idea. If you're trying to figure out types of students, if you change the type of latent variable from something continuous to something that's discrete, something that's nominal, name only, you get that type of information. You can get that type of information. All of it's can, it's all hypothetical. You got to actually do it with the data. How we doing? So it turns out, this is the crazy thing. There's all these names out there for these models, right? There's CFA, IRT, IFA, all that stuff. And we throw in some other things. All the CFA, IRT, IFA, all that implies a continuous or interval level trait. But then we start getting to other names like latent class models or diagnostic models or cognitive diagnosis models. None of that talks about the items, they talk about the trait themselves. So you can see at some point we're going to have to throw the names out. What we're going to have to focus on are the features of the models, the variables, the distributions, and their assumptions. And that's where we're building with this. How we doing? Okay. One of you I know has a project where we're going to have to combine an ordinal level and an interval level on different types of data. What are we going to call that? Probably crazy. All right. Other questions? You okay with my rant about like why we do this? I didn't even see that coming. Anyway. Okay, so the most common that we're going to do, and the focus of most of the class is on these continuous latent variables. I actually think those are ideal in many ways because you do get the most information. However, the trade-off is the variables you observe that they're related to can give you only little bits of it. So you have to have a lot of time and a lot of precision to be able to do this. So as these traits don't exist, these continuous latent variables need a metric. We need to understand where their location is, what their scale is. What's their mean, their location? What's their standard deviation or variance? And so defining that metric is the first step in defining a latent variable model. I call this scale identification. Right? We are literally trying to set what the milestones on the scale is. And it's not the case where everything has a mean of 0 and a standard deviation of 1. And here's why. So the metric's arbitrary, first of all. So you may have learned in IRT that the mean is 0, standard deviation is 1. That actually works really well in a lot of measurement contexts. I'm not dissatisfied with that. However, if you're aware of the problem of secondary analysis with data that have error in them, imagine what would happen if you wanted to predict that latent variable, if that latent variable became an outcome in a structural equation model. And you know that structural equation models are actually built because of the issue with unreliability. We're trying to estimate relationships or regressions effectively among the latent variables or among other observed variables in the latents simultaneous so that the impact of reliability does not filter and bias our parameters of those relationships. So you said, I'm aware of this. I want to know whether, let's say, a STEM major, are you a STEM major or not, whether that impacts your GRE score. How's that sound, right? Do STEM majors have higher GRE scores than non-STEM? I know you're giving me the eye. I'm looking for a...
There's a big debate about what constitutes STEM or not.
I understand that. I'm looking for here, let's do it this way. Those with training in psychometrics. Right? I'm just looking for a binary variable to give an example with, right? So your outcome is theta, the latent variable from IRT, and you're predicting it. If you identify its scale in the measurement process, having a standard deviation of 1, though, there's a big problem. Think about linear regression. You have y. You fit an empty model, which Lisa likes to talk about, right? No predictors. The residual variance, there's no residual. The variance of y is its residual variance. You put in a predictor, what happens to the residual variance? Reduces, so long as the predictor's related, right? If you fix the scale of the theta in IRT to 1, and you put it in that simultaneous regression, it can't be reduced. You can't shrink the scale of it because it's already fixed to 1. So that's the motivation for having different types of identifications. So a standardized latent variable works great if you don't want to do a simultaneous analysis with it for some other reason. But when you do need to do that, and you want to do that in a way that tries to do the best when it comes to not having bias based on the error to it, you'll need to go and allow that variance to be an estimated quantity, so you can at least talk about how it's reduced. And there's a way to do that with data to make that work. It's the same identification that we'd have in a factor analysis. Basically, we take one of the discriminations, we fix its value, and that allows us to have the amount of sort of math to work out to allow us to estimate the standard deviation or variance of theta itself. Now, it's, again, arbitrary. And that variable you pick to anchor it will anchor it around features of that variable. But it's still, it's arbitrary, meaning that whether you fit it that way or you fit it with the standardized without the simultaneous, you'll get the same model likelihood. And the results are transformations of each other. So whether you fit it with a mean and standard deviation. What I want you to know is that the mean and standard deviation part is great. It's fine, but it's a choice. You don't have to do it that way. And that's the key in this, right? There are very valid reasons for using it, particularly with operational psychometric, scale development, scale administration, and so forth. How are we doing? Yes?
When we're talking about a continuous variable, are we talking about the actual variable having a continuous distribution or the data that we're collecting, basically?
This is the latent variable that we're trying to measure.
Okay.
It's the pretend thing.
Okay. If I measure it with a non-continuous.
We can still have it that way.
Okay.
Yep, that's a very good question. I'm glad that you asked that. This is all about the pretend.
Okay.
Because we're hypothesizing this construct, we have to sort of pretend its features as well too, right? The unicorn argument, I believe one of you mentioned to me, right? We're sort of describing the features of the unicorn here as we go forward. So we're going to try to build an analysis where, regardless of the observed data, we can still assume this about it. Hope that helps. Other questions? Thank you for the question. Okay. Anyway. So yes, the metric is arbitrary. For most choices, it will lead to the same model fit, the same likelihood value, the same posteriors, just a different location, all the parameters can be changed to map it onto a different metric. So oftentimes, this is where I want to take the moment to introduce path diagrams. So a lot of Bayesian uses path diagrams. A lot of psychometric uses path diagrams. And then there's all sorts of somewhere in between. So this is our first diagram I want to show you, because diagramming things can help us understand a little bit of it. It provides a quick way of looking at a measurement model. It's not always perfect, but it's quick. So in a path diagram that comes from a measurement model or structural equation model framework, okay, these are all graphical models. There's actually 3 I'm going to have to talk about this in this class, which adds to the complexity. This is the first. It comes from SEM. I think that's where it started. The second is something called a Bayesian network. Turns out all of these are Bayesian networks, but it's a little bit different. And the third is a Bayesian graphical model, which actually is more specific than any of these. So all of these are things that you're going to read, particularly if you're trying to understand Bayesian, that adds to confusion about what these mean. So this is the first type, and it's only about the latent variables and observed variables. Okay? I'm going to call this path diagram to denote it from some of the other graphical models that you'll see. But generally, the latent variables in a path diagram are represented as circles or ovals. That term, right there, there's a latent variable. Boom. I need the sound effects. In a graph theory approach, those of you who understand or heard of graph theory before, there's a whole mathematics of graphs and everything. That variable itself will be called a node. That language gets used in Bayesian networks, which is a type of data analysis and psychometric procedure. So latent variable is a circle. Any variable is a node. So on the next slide, so the latent variable I'm going to replace with a theta, and then I'm going to put in observed variables. Those observed variables in these diagrams get denoted with rectangles or squares, usually. And I'm going to denote these as y1 through y5. If you remember that survey we started the last class with, think of those as the 5 either numeric responses or categorical responses to that survey. And here you have it. So what do we have here? The latent variable, the circle, is right here. That's theta. The observed variables, the squares or rectangles, are over here. In a graph theory sense, these are all called nodes. Everything on here that's in a box or circle is a node. And then you see arrows. The arrows right here have an arrowhead. I'm sorry, it's kind of small here, but the arrowhead is terminating at the square or the observed variables and emanating, starting from the latent variable, ending at the observed. So it's a direction. So what this is doing is trying to quickly describe the direction of the relationship. This is sort of implying that the variable theta is related to or can be used to predict the variables y1, y2, y3, y4, and y5. That's what it's saying. How we doing? You've seen that before. Okay. The arrows, by the way, those lines are called edges. So a graph is made up of a set of nodes and a set of edges. Kind of odd language, but it will keep showing up when you hear about it. For us right now, all we need to know is variables, either latent or observed, are nodes, and the relationships are the edges. So here's the thing, though. I used to be really mad when I saw path diagrams because I'm just artificially mad about random things, right? Evidently I'm just, in addition to being uninteresting, just really unhappy. I'm not, that's not true. Things set me off and I don't even realize it. But the problem I had with it is that diagram itself, you say, this is my model. It's actually not a model. It's a schematic depiction of the model. Because it's not, it doesn't show, for instance, all of the model parameters. It doesn't talk about the distribution of the variables, right? That's which is especially important for Bayesian, right? So because of that, you can point to the path diagram, but this could imply an IRT model, a CFA, or something in between, right? You don't know. All this is laying out are the set of variables, which ones were observed, and which ones were latent. So far, so good? Right. If we were to go and actually provide the mathematical parts of it, that arrow, okay, we have to, again, pretend the latent variable is an observed variable. The arrow, which is called the edge, indicates that one variable predicts the other, right? The part of the line that doesn't have the arrowhead is the predictor. The part of the line where the arrowhead ends is the outcome. Okay? So if we were to assume the outcomes, y1 here, were continuous, what that graph, that path diagram is implying is that for a given variable, there's a linear regression of the circle predicting the rectangle. And this is where Lisa will tell you I like to say circle plus square doesn't equal triangle. Right? This is the model right here. This is part of the model. Pardon me. We still didn't define distributions and all that other stuff, right? That's part of the model. How are we doing? Okay. Turns out, because there are 5 arrows, there are 5 regressions simultaneously. Right? One for every one of the items. By the way, the notation here, y is the thing we observed. The P stands for person, the person who gave you the data. The second subscript is which one? 1, 2, 3, 4, 5. You can think of those in order of the survey that we had given out at the beginning. Beta, the first subscript is for which outcome. The second subscript is which parameter on that line. So beta 0 is often what we think about as an intercept. This is the intercept for the first outcome. That's what that says, right? We actually have 5 intercepts with 5 regressions. Beta 1, beta y1 comma 1 is the slope predicting y1. Right? And this is all in regression language, right? This is pretending the latent variable was observed. That path diagram is telling you, if we had observed it, we are basically wanting to estimate a multivariate regression where we have 1 predictor and 5 outcomes. Right? You often don't see multivariate regression because it's usually kind of a waste of time, but if you took a multivariate class, you'll hear about this, particularly from a least squares point of view, but it's possible. Uninteresting, but possible. Uninteresting in that there's nothing added if you were to do this 5 separately versus 5 at once. I mean, I guess there's a multivariate test you could test to test all the parameters at once, and we can map that onto something we call Wilks Lambda. Wilks was a student here, I believe. The PhD dissertation was in Lindquist was one, either on his chair, with a chair or otherwise. So you can there is stuff that's important to us who study this, but from a practical point of view, it doesn't really change a lot from the regression. So let's do some interpretation. Question?
Are there path diagrams for nonlinear relationships?
gets harder. No. And that's the hard part. People will try. They'll have like a squiggly line. But there's only so many ways that you can be nonlinear, right? Not to mention there's curvilinear lines that talk about like correlation or covariance, which are relationships that don't have a direction, right? So it gets, the nonlinearity is difficult to represent. Another thing that throws path diagrams off are multiple dimensions of sampling. So right now we could actually think of this as 5 item system as one person, so we've got like a 2-level model. If you have a 3-level or a cross model, good luck notating that. It's going to be very difficult with a path diagram. So let's do some interpretation, shall we? I know this sounds really lame. You're taking Bayesian psychometrics. I'm telling you to interpret basic, simple linear regression. But there's a point, because those interpretations will follow us to psychometrics, all right? What's the intercept? The expected value of y when theta is 0. Theta being 0 knocks out that part. Right? What's the slope? The expected increase in y for a 1-unit increase in theta. Or I shouldn't say increase. The expected change in y, because that slope can be negative, right? That's the expected change in y for every 1 unit of theta. Familiar? Comfortable? We're aces at regression? Good? Because guess what? Wait, a couple more. Almost there. I'll say guess what in just a moment. The error term is the expected difference in the predicted score from person B to person I. Now we often assume in linear regression that each error follows a normal distribution, the mean of 0, a variance, a sigma squared error. That variance sometimes goes by different terms. Sometimes we call it residual variance. Right? We call it mean square error in different contexts. But basically it's how far off our prediction is, right? It's indicating how that works. And so if we're all doing this simultaneously, we get multivariate regression. So it turns out, what is the distribution this implies about the outcome? Actually, go there.
Normal.
Yes. This error is normally distributed. We think about it this way. In our linear regression sense, beta 0 is a constant. So this is the line conditional on theta, right? So it's actually conditional on these values, but conditional on each of these things. This is a constant, this is a constant, that thing is a constant. So the only thing that has a distribution is error. So y gets that distribution, and that turns out to be normal. What is the mean of that distribution? Well, if we took the expected value of all of this, we would see that the expected value of this sum, because these are constants, they get pulled out of the expectation. Okay. Expected value, actually, we could actually separate the expectation. Sorry, we can distribute it across the sum. That's expectation of a constant is itself, constant is itself. Expectation of error is 0, it's its mean. So the mean turns out to be that part of the model. The intercept plus the slope times the predictor. What is the variance then? Again, we can use an algebra of expectations. The variance is the expected value of a variable minus its mean squared. Maybe we can do the mathematical statistics if we really wanted to, but I'll just tell you it. Because these are constants, they do not impact the variance. Right? So we're left with the variance of that thing is the variance of y. Turns out that's sigma squared error. So now we're saying that y has a normal distribution where the mean of it is intercept plus slope times predictor, and the variance is sigma squared error. And now we're to the part where we can put this in a Bayesian analysis. Because now we have a model that's specified from the linear predictor down to the distribution. And that's the key of thinking about this. We got to go a step further than the model itself would say and think about what the distribution implies. So y would follow a conditionally normal distribution, and I can actually show that real quick. What that means is if we were to, here's our normal distribution. Oh my goodness, I'm out of time. I'm going to stop here. Sorry. Thank you. Let's turn off everything. If you have more questions about this, see me after class. I'm here for office hours for a couple hours. All right? Thanks, everybody, for being here. It was great to see you. Hope to see you Friday for 50 minutes. Have a good rest of your week until then. Thank you.